Okay, so let's get started. It's 1:32. Okay, so the first lecture today is on normalization, and the second, if we get to it, will be on probe effects for microarrays. All right, so in both cases, the data I'm going to be showing is microarray data. The second generation sequencing data, we are seeing similar issues as the ones I'm showing today. We might have a lecture on that later, especially with RNA-seq, where some of the same issues are coming up that we're going to describe today for gene expression arrays. Okay, so I'm going to start off showing you some data from 5 technical replicates. These are 5 box plots. Each one comes from a different array, but they all have the same RNA on them. And you can see that they are different. You can see that the distributions are different, the median is different, the range is slightly different across the 5. And again, this is the same exact RNA on 5 arrays. This is a very common problem. You will see it in pretty much any high throughput technology, at least the ones I've seen. You put replicates on 2, you measure the same thing twice, and you get overall global differences. I'm calling these global differences because it's a whole shift up or a change in the range, things like that. I'll call global changes. So this is, if you get data like this and you compare A and B and you just do it blindly, you will conclude that pretty much every gene is has higher expression in sample A versus B. That's obviously wrong because these are the same samples. This is very common. You will always see that. You have to deal with this first. Most manufacturers know about this, so they have their own way of dealing with it. So one of the first approaches to this problem with microarrays was to simply make the medians match. Right? So we're doing now this statistically, right? We're not going back and redoing the experiment, changing the properties of the experiment so that you get more or less expression. We actually do it on a computer. And that's when we start calling it normalization, when it happens on a computer, when it happens on the data, as opposed to changing the experiment. So here, a very simple solution to this is to take the median of each array, right? So the median is actually shown here with the horizontal line, and you make them all the same. We can make them all 7. So you subtract the mean and add 7, and you're done. And now they all at least have this global property of the median is going to be the same. Now I'm going to show you why that approach is better than nothing, but it not always works very well. I'll show you what I mean by that. All right, we're going to slowly get to why it's a problem, why problems can remain. This one is the same arrays, but now instead of showing you a box plot, which summarizes the data into 5 numbers, right? Median, the interquartile range, and the range. This one is actual histograms of each array, right? So you can see there's 5 histograms there, and they're really estimates of the density, which I just call them histograms because in a way they are histograms. And you can see that you can see how the medians are different, but there's also a little bit of a difference in the distribution. Like if you look at the solid green line, that one has like a second bump right here that the dotted pink line doesn't have. The dotted pink line doesn't have that protrusion, and in fact, even though it's higher in this part, then it's lower here. And so it's more than the median that's changing. These are technical replicates, and then the distributions are different. Okay, yeah?
How about some manufacturer like Illumina, they say they have negative control
Yeah.
on the back and they just use those replicates?
I'm going to show you a picture of how that works. Yeah, so negative controls is one way to try to fix this. I'll explain what that means. Okay, so now that's at the global level where we see big differences that are not that hard to fix. But now I'm showing you a picture where we can see a little bit more at the local level, at the level of genes. So So this is a plot of two of those samples. Well, it wasn't those two, but two replicates with spike-ins. This is from the spike-in experiment. So you can see the red. Well, where's my arrow? There it is. The red dots are genes that were spiked in at twice as much, right? So they should be, these guys should be differentially expressed. The rest, which are mostly here, right, where the blue cloud is, are not differentially expressed. So this blue cloud should have an M of 0. So you can see there's a problem, right? You can see that these guys are not 0. They're 0.25, and in fact you have some, some of them go as high as almost as high as a full change of 2 at the bottom end. But once you go up higher, that problem turns into the opposite, where you have the other sample is now higher. Genes in this area have a higher expression on the other sample, so it changes direction. So if we change the median, let's say we made the medians of these arrays the same. If that's the approach we take, what would happen to this figure? How would it change? If I change the medians of the samples, how does this figure change? Think about that for a sec. Does it straighten out that shape, that curvy problem? What happens if I make the median with the first one 10? And then I leave the second one at 6? What happens to this whole figure? What would happen? So what happens if I add 10 to this first sample and leave the other ones without change? What happens to this? It would shift up. Okay? The whole thing would shift up because I'm adding 10 to all the genes, not just one, all of them. I'm fixing the median. That means I'm adding a number to every single gene. So as I change the medians, all I do is I move this thing up and down, and I don't change its shape. That's the problem. The median fix does not fix this shape. So by the way, maybe I assume that you understood the problem, but the fact that this has a curve in it is bad. It's not good. We don't want that. They should be. We'll accept noise. We'll accept that all the genes that are not supposed to be different are not exactly 0, but at least they should be around 0. Right? So this is a bias that we just can't have. If we have that, if we keep this bias, we're going to get all these genes here that are supposedly differentially expressed, and in fact they're supposedly differentially expressed more than these guys here, which are actually differentially expressed. So we somehow need to get rid of that bias, that shape. And I also want to make another point about the power of making MA plots. This is the same exact plot, the same data, exact same data on a scatter plot. Do you see the curve? Do you see the bias? You don't see it at all. You only see it when you rotate it, and the reason that you see it now is that you're actually spending more of your real estate on the plot on the axis that matters, which is the difference. Here we're spending all our plot on we're putting all our pointing to the diagonal, which is not really informative. We want to see this dimension, the difference. Okay, so that's what we need to fix. This is a very common problem. You will see it in all types of platforms. And this data is not background corrected, right? If we background correct, we can get the problem we saw last time where the variance just gets big. Okay, so what have been proposed solutions to this problem? So in this picture, I'm showing you, again, this is the same kind of plot, but now the first plots were from an Affymetrix chip. This is from a 2-color array. So it's a different platform, and you see the same thing again. It's just going down, up and up. It's going up instead of down, but it's the same problem. We see a curve. So the manufacturers include housekeeping genes to try to fix this. Now here, at least in the early days, and this is a mistake that a lot of them still make, look at the housekeeping genes. It's the yellow ones. You see them up here? Those are the yellow. Those yellow genes are supposedly housekeeping genes. What does that mean? These are genes that are not supposed to change from sample to sample. So you use biology knowledge to do that. You pick genes that are no matter what cell you look at, they should be expressed in the same way. And biologists have a list of genes that they use for this, and there they are. Okay, now, and what is the trick then? Once you have this group of genes and you measure them, you can take their mean, and that mean should be 0 because they shouldn't change. So the difference between the two samples for those genes should be 0. If we do that, it's not going to help fix our curve, right? It's just going to make it go up and down again. We're just adding a constant to the whole thing. So we could try to fit a curve to the yellow points and remove the curve, but the problem is that the very common problem with housekeeping genes is that they're highly expressed, so they only cover the high part of the dynamic range. So all the yellow genes are up here, and our real problem is down here. That's where we need to fix, and we have no idea what to do here. There's no housekeeping genes there. So how about those blue genes? Those blue genes look good, right? Those blue genes appear to be following the shape, this shape that we want to get rid of. So those blue genes are actually, it's a statistical algorithm that has found them. There's a statistic. I think this one is done with an algorithm developed by Wing Wang and Cheng Li that identifies genes that look like control genes, but data driven. You don't ask a biology, you ask the data, and you pick these. So that's a paper I can refer you to later, but it's one approach. Now the red line you see there is made using a procedure called Loess, and I'm going to talk about that a little bit later. And that's currently, I would say, is the most standard way of fixing this problem. You basically fit a Loess line, and you fix the problem that way. All right, so we're going to discuss a couple of approaches to normalization. So here are some of the solutions for Affymetrix arrays. I should be more general than that. For arrays that are single channel, not two color, single channel arrays. So Affymetrix, Nimblegen, some of the Agilent arrays are like this. Okay, so these are the solutions that are most widely used. I would say the most common one is the first one I'm talking about here is to force the distributions to be the same. That's called quantile normalization. Those are two papers that talk about it. Another approach is to fit curves to the data like the one I just showed you, and to remove these effects. And there's a few papers that I'm listing there that do that. And then the third approach, which I won't talk about too much because it's a little slightly more complicated than the other two, is to do an adjustment based on additive/multiplicative models. I'll refer you to these three papers that describe this approach. This paper by Huber et al. Describes a procedure called VSN, variance stabilization normalization. That's quite popular, and there's a bioconductor implementation that is very nice, very fast, and it's a little bit more complicated than the other two. So I don't know if I'll have time to describe it today. And then among these guys, the most common name that people use is Loess normalization, and the most popular implementation that I know of is in the Lima package in bioconductor that implements this. Okay. So the first one I'm going to describe is quantile normalization. It's perhaps the most popular approach in single channel arrays. But I should say that all these methods perform very similarly. They all do very well, much better than the medians approach or the control genes approach. Now, quantile normalization is very fast and very easy to code, and it's easy to understand what it's doing. So I like it because I use it a lot. I use it a lot, not just in microarray data. I use quantile normalization in many other types of data. Okay, so here are the 4 steps that you follow, and I'm going to use a little illustration to show it. So here is the card. Oops, sorry. Okay, so here's your original data. Rows are genes, columns are samples. And they don't have to be genes, they could be probes from a SNP chip or methylation array, from sequencing, counts from sequencing, whatever you want. It will work just the same. So notice that if you look at these, this is the gene, and I'm using color to distinguish gene as well, because we're going to shuffle things around a little bit later. So look at the first array and the second array. If you just look at that data and then look at the third, actually the third, yeah. So the first and the third, if you look at those numbers, how would you describe them? How would you say the third compares to the first? The values are smaller, the same, bigger.
3 times as much in the third.
They're 3 times as much, maybe a little bit less, but they're bigger in the third than the first. All of them are kind of like that, not just one gene or another. And then the middle one is more comparable to the first in global properties, but there's maybe you don't really see any gene that's that differentially expressed, but 6 versus 4. But here's 8 versus 4. Well, the way I set this up, just to motivate quantum normalization, the first and the third array are replicates. They're supposed to be the same. The way I set this example up. And we're going to see how quantum normalization gets that back. So what is the idea? What I want to do in quantum normalization is I want every column to have the same distribution. So in a way, that's like the median approach taken to a next step. So the making the medians the same takes each column, and it says they all have to have the same median. That is one of the quantiles. The median is just one, the middle one. I'm going to make all the quantiles the same. So I want the smallest number here and here to be the same. That doesn't say that these 2 genes have to be the same. These 2 values have to be the same. It just says that the smallest value has to be the same. The second smallest value has to be the same. The third, the fourth, and the fifth. All of them have to be the same. Right? So again, I'm not saying anything about genes having to be the same. This is where I think people get confused. They think quantum normalization makes genes all have the same expression, but that's not what happens. It's the overall distribution that is the same. So here we go. First step: order the rows for each column. Right? So we have them ordered: 2, 3, 3, 4, 5, 3, 4, 4, 5, 6, 4, 8, 8, 9, 14. And now the rows are no longer genes. So look at this gene ended up here. And this red gene ended up here. Okay, the genes are now somewhere else. I have them ordered though. So now I can see the distribution very clearly for each column. In the next step, I'm going to average these numbers. Each row I'm going to average. Right, so now I have 3, 3, 3, 5, 5, 5, 5, 5, 5, 6, 6, 6, 8, 8, 8. So they have the same distribution. I just made it happen. I just did it. I just forced them to have the same distribution. But there's one remaining step, and it's to bring them back to their original order. So now I'm going to go get all the light blue genes and put them in the first row. So there it is, 3, 5, 3. Then the greens. So this one comes here, and this one comes there, and that one goes there. 8, 5, 8, etc. So now this is a quantile normalized version of this table. And look at the first and the third columns now. You see how they're practically the same? 3, 3, 8, 8, 6, 5, 5, 5, 5, 6. They have been made to be the same, but the second and the first are actually quite different. So for example, this gene is almost a twofold change, and so is this gene. So I didn't make the genes have the same values. I made the distributions of each column to be the same. That's what we did. Okay, any questions? That's quantile normalization, and you can see how easy it is. You can write this, you can code this up in R in a few lines.
But you use the same color to, you order and average these two.
Yeah,
The
uh,
same color represent.
genes. Color is gene. Color is gene, or if you want to think of it this way, row in the original matrix. So blue is 1 in the original matrix. Yeah?
What if the second, third, the 14 number is the real, biological real, and wouldn't you lose the...
So you're saying, what if 14 is really that much bigger?
Yeah.
Yeah, that we would lose it. If the 14 is supposed to be a 14, we would lose it. But if the 14 is really a 14, I'm going to have a hard time believing that, because every single gene is about 2 to 3 times bigger. So what happened? That must be an effect of that must be a technological effect, not a biology effect. It's not like that's the only gene that did that. All of them went up. So you maybe had the amp too high, or you put too much RNA on it. That's a much more likely explanation. That is a fair concern. It could happen, but my experience is that it's almost, I shouldn't say almost, in all the examples I've looked at, maybe there's a couple of exceptions. Yeah, so with cancer, sometimes there's an exception, but most of the examples I've looked at, it's better to do quantile normalization than to leave it as is. Because what happens is, sure, you may lose some real biology, but mostly you're removing so much unwanted variability that would totally confuse you if you left it in, that it's worth it. But it's important that you keep in mind that is happening. If, for example, you're comparing cancer and normal, and this particular cancer, what it does is it makes genes in general get expressed, you will lose that. But what you won't, if it's just 3 or 4 genes, you won't lose that. Those will stay, because it's a global change that you perform on an entire set of probes. And by the way, on an Affy array, we do this at the probe level. So you do this to what is it these days? Millions of points, not just 5. 5 is the example I'm using to illustrate it, but usually you do it on all probes, not just a few genes. Okay? All right, so here, now let me show you real data so you can see how it doesn't remove real stuff. So this is the original data, and remember, the blue is supposed to be the same. The red are real differences. And here, this is before Quantile, and that's after. So see how the red stayed big? That's not surprising, because we took the entire array and changed its distribution. But those genes remained high relative to the other array. So that's a very typical fix that happens when you do quantile normalization. You go from something like this that has a weird curve that's giving you false positives, and get rid of the curve, but keep the real signal. All right, now that's for the one channel arrays. Is where Quantile is very, very powerful and popular. For 2-color arrays, you could do quantile normalization, but the fact that there's 2 colors on a physical piece of glass makes you think that perhaps we should take advantage of the pairing. And it does look like it is more powerful to do that. So what I mean is, if you have some kind of artifact that is affecting one specific slide, like the spots at the top are stronger than the bottom, the pairing, the 2 colors will be affected in the same way on that chip. So you want to take advantage of that and make that correction at the single array where there's 2 colors level. So when you do that, then Quantile isn't appropriate anymore, because you want to normalize every pair of colors instead of taking everything in Quantile normalizing. Okay, so that's what I just said. All right, so one early approach to this was ANOVA. This is maybe one of the first papers on microarray data analysis, but they didn't take, as far as I could tell, they didn't really take care of the nonlinear effect, which made it not that useful for that purpose. So they did that same group actually later had an approach that did take into account that different arrays could have different backgrounds, and that could that could explain the curves, and they try to do that to fix them, and it does work well, and it's the fundamental idea behind the additive multiplicative model. Let me explain what I mean by that. So background correction and normalization are related in a sense. So the typical curve we see looks like this. It's very common. You just saw two of them. Actually, three. I showed you three examples, all real data, and all of them had that same shape. It's a curve that kind of levels off towards the high end of the A values. So if you want to, you can recreate that curve on a computer by modeling the red and green channel as a signal that's the same, and adding 50 and 100 to another. So you add different backgrounds to the two levels. So if you're adding a constant, why is it that it curves? If you're just adding a constant, shouldn't that just make like a line go up and down? So what is it? Why is it curvy instead of just the line shifting? See if someone notices that subtlety. All right, so R is 50 plus S. The green channel is 100 plus S, and that results in a curve like that. So there's one little missing part that I have explained it, but let's see if you catch it. What is M? It's the log ratio. So if you have two constants added to a value that has a range of, in this case, 6 to 8, you can do it yourselves and convince yourself that that's what you're going to see on the log ratio. And to understand why that happens, when S is 6, when we're down here, so when S is 6, what do we have? We have 106, we have 56 divided by 106. That's about 2. Take the log minus 1, right? Because it's 1/2, really, not 2. Okay, now let's go way up. When we're up 14, we have, what is that, 4,050 divided by 4,100. That's 1. Take the log, it's 0. That's why it curves like that. The lower the S, the more of an effect the 50 and 100 have on the ratio. So if you can somehow correct the background, you will get rid of this curvy effect. But last lecture, we saw how hard, in the background correction lecture, we saw how hard it is to correct for background. So in practice, many people don't background correct and instead normalize these curves away. That's the most standard approach for these two color arrays. So this is I would say the most popular approach. This is the one that's implemented in Lima, but there's various people that have wrote on it. I call it in general the M plus bias approach, where you estimate the bias and remove it. So we assume that the true cloud should have what you're seeing is the M values plus a bias, and the M values, if it weren't for the bias, should be a cloud around 0. So you're making an assumption, just like we did for Quantile. We're making an assumption here. It's a different assumption. If we assume that the cloud of points is around 0, what are we assuming about gene expression in the two samples? What is the biological assumption that we're making? What's that? Well, okay, be a little more precise. There's no global. On average, most genes, well, so there, I'm sorry, I guess that was better than what I said. There's no gene is different. Most genes are not differentially expressed. So on average, the cloud is around 0. So that's an assumption that you need to be okay with. That's a different one than assuming the distributions are same. I would say it's a similar assumption and to the other one, but it's not quite the same. But if you think there's many genes that are differentially expressed, then this won't work. So now what we do is we assume there's a bias and we try to remove it. But how do we remove it? We have to have an idea of what's causing that bias. So there are this doesn't happen as much as today, but in the old days there used to be all these things like print tip and plate effects and all kinds of other effects having to do with how non-industrial the production of these chips were. So you would model biases based on these things. These days, the one that we look for by default is the effect of the A intensity. Right? So we see that the curves change with A, and we try to estimate that. So it's easier to just show it with a picture than to talk about it. So here's a picture we saw at the beginning. So here's the M. We assume that M should be a cloud around 0. So in our heads, we see like this curve, and that's the bias that we want to get rid of. So that line is a bias that depends on A. As intensity changes, the bias changes. So we assume that is a bias. We're going to try to estimate it and get rid of it. So now I drew a line there, but how do you actually draw a line like that? It's not a line, really, it's a curve. How do you draw that curve automatically? If we're going to do this for 1,000 arrays, we can't go in by hand and do it, right? We need an algorithm to do it. So the most popular approach in the microarray world to estimating that curve is to use something called Loess. It's short for local regression, local weighted regression originally. Used to have a W there. So there's an R function called Loess that does it kind of automatically. It's very nice. I'll show you. I explain how Loess works. It's a very powerful technique for estimating curves. Okay, so I should say that in the statistical literature, there are many ways of estimating curves. Many approaches have been described. Splines, kernel smoothers. There's many more. Loess works really well with microarray data. I think some of the others would as well, but it's kind of set itself as the default and people just use it. But basically the problem is you have a cloud of points, like those purple points there, and you want to estimate the curve that our eyes can see. There's a curve, you can see it going through there, but how do you actually get it? How do you automatically find it? So if we fit a straight line, we're not going to get it, right? If we fit a line, it won't be like that. If we fit a parabola, it won't be like that either, right? That's not a parabola. Parabola goes back up. A 3-degree polynomial would not go through there either. That would go like, it would have a wiggle like that. So these functions that we know that we can write down don't really work here. A spline would catch it, and as I'll explain, this local regression approach catches it too. So let me explain what the idea is. So in mathematics, there's a famous theorem called Taylor's theorem, Taylor's expansion. So if some of you learned that in calculus, maybe, how many have heard of Taylor's expansion? Do you know why it's useful? Nobody knows why it's useful. For after 5 years, you'll finally find out why it's useful. So Taylor's expansion basically tells us that any function, with certain properties, but for us humans, any function, if you look at it close enough, if you go very close, in a small little piece, that function is a polynomial. That's what Taylor's expansion says. Okay, so now let's make it even. There's another level to Taylor's expansion, and it says if you can pick a polynomial, you can say I want to do parabolas. That as opposed to say lines, as opposed to straight lines. Well, what Taylor's expansion tells us is that if you want lines, you have to actually go a little bit closer. If you want a parabola, then you can expand out a bit. But it doesn't matter which one you choose, you can always get close enough if you make the window you look at small enough. Now, we see Taylor's expansion applied every day. If you have seen gardeners work, well, they make a edge where they make beds. The beds are curvy, right? You look out the window. Well, not at Hopkins, but somewhere where there's grass and gardens, maybe Homewood, we could see these curves, right? It's a circle. They have ellipses, all kinds of curves. But what instrument do they use to make these curves? What? Shovel. like a shovel, which is a straight line. Right? So they take a shovel that's a straight line and they make any curve. That's Taylor's expansion. So here we're doing the same thing. We're looking at this picture and we're looking at a small window and we're saying in a small window that thing is a line, like that little section. So I just colored in brown a small window, and in that window I'm going to assume that the curve is a line inside that window. And it does look pretty linear, right? Look at the pink. It does look like a line, doesn't it? You could, if you want to be a little more flexible, you could do a parabola. But I think a line is good enough here. So what I'm showing you with the, what color is that? Magenta? Magenta dashed line. That is the line that has been fitted to the gray points using least squares. That is the line that best fits those points. So you can see that it fits the line, and what I'm going to do is I'm going to keep the middle point that I've just fit. I'm going to keep that and say that is my curve in that point. That is the purple, that's going to make the purple line. And now I'm going to move to the right and I'm going to put my shovel in another part of the garden. And I'm going to do the same thing. I'm going to fit a line and I'm going to keep I'm actually going to do this for every point. I'm going to go point by point, moving my window and fitting a line, and at the end I get that curve that disappeared thanks to PowerPoint. And at the end I get that curve. That's how Loess works. Yeah, questions?
Will Loess come up with an equation or a function?
How do you call Loess? What is the question?
Will that come up with the equation or function?
Oh, does it come out with a function?
Yeah.
Okay, yeah, so, yeah, good question. So do you actually get an analytical function that you can write down? And the answer is not what you're thinking as a function. You do not get that. You get a function in discrete space. Any pair of points is a function, right? For every x, you get a y. That's a function. But you can't write it down like x squared plus 2x. That you cannot do. With splines, you can. With splines, you actually get a very ugly, but you do get a function. So that is an advantage of splines over Loess. You get an analytical function with splines. With Loess, you don't.
So that means this curve can only be visible. It's not something analytical.
It is, yeah, right. Well, you could actually write down x and y, and you can see the numbers. But you're correct. It is in the computer. It is a function. You give me an x, I give you a y. That's a function, but you cannot write it in a nice little formula thing that makes things simpler sometimes. Yeah, question?
So how does it compare to the spline regression?
So, yeah, so it's very similar. If I use a spline and I choose the degrees of freedom in some way, I will get practically the same exact curve. So why do we use Loess? Why do I think Loess has beaten, in quotes, splines in the microwave world? I think one is because Loess has built into it a robustness to outliers. So if there's some, let's say the differentially expressed genes are going to be points out very far away from the cloud, and you don't want those points to pull your curve up, right? So let's say there were like 20 differentially expressed genes up here. This line could come up and by mistake, because those are real. Those aren't part of that bias. So Loess has built into it. I didn't explain it, but it has built into it a outlier robustness procedure where you fit it once, detect outliers, give them little weight, refit, detect outliers again, refit a third time, and actually you can have it do it many times so that it doesn't count them. The other advantage that I find with Loess, when the points are dense like this, you don't have to think about knots. So, but that doesn't really make a big a difference.
The whole line is not a smooth line.
Yeah, it's a smooth line. It is, but you don't have. What I'm saying in splines, you have to pick. You have to pick knots. Depending how you pick the knots, you can get different answers. But again, if you use a spline here in R and you use like 2 or 3 degrees of freedom, you get pretty much the same curve.
So in Loess, do we need to specify the degrees of
Yes.
or the order of the?
Good question. Good question. So those that aren't following the whole knot situation, you have to understand what splines are, and I won't get too much into it right now, or at all. But I will explain. It brought up a question, and is that there are choices to be made here. For example, an important choice is the window size. We have to pick that. Right now, what's the window size there? It's like 1/5 of the data. I can make that 1/3 of the data, 2/3 of the data. The more wiggly I think the curve is, the smaller I have to make the window size, because of Taylor's expansion. Now, the smaller I make the window size, the more variance there will be in my estimate, because I have less points to estimate the lines. So there's a trade-off that I have to put up with. Here I used about 1/5 of the data as my window size. And Lima has already chosen that for you, because they have seen a lot of, the authors of Lima have seen a lot of arrays. But you can change it. If you think you need a smaller, a smoother, or a less smooth curve, you can change it. So those are choices that you have to make. And by the way, that's another nice thing. Now this is more of a technical thing, but another thing I like about Loess is that this is a very practical preference. That what you specify is the percent of data that is going to be used to estimate the lines. You don't have to think about window sizes and units of the x-axis or where to put the knots. You just say, use 10% of the data, use 5% of the data, use 20% of the data, and it just goes and does it. I somehow have a better feel for what that means than actually specifying window sizes, like saying, okay, make a window size that has 10 or 4, window size of 4. But what if A changed? Right? What if A all of a sudden is wider? Now that doesn't mean the same thing anymore. Any other questions?